Hi folks, I'm Mr. Schrago, and I'm going to be taking you through the notes on pages 2 through 3 on free body diagrams. So on these pages, what we're going to be doing is talking about FBDs, free body diagrams. They're going to be something that is going to become very normal to you throughout this unit. They are a way that physicists can represent all of the forces, or pushes or pulls, that is, on an object without having to draw whatever is causing that push or pull. This is really handy if you're like me and you suck at drawing. It's something I've worked at getting better at, but still I like the opportunity to just break something down to arrows and boxes. Whenever we're doing free body diagrams, one of the things we have to do at the very start is always ask ourselves, what is pushing or pulling on the object that I'm trying to draw a diagram for? Now, you have to think about both up and down motion, and then you also have to think about side to side. Now, standing right here, sitting still, there's really nothing pushing me side to side. Right? My dog's laying on the floor over there, and if she came and leaned on me, I'd have a force pushing me to one side, but she's not. So, side to side, I can say, well, I don't really have anything pushing on me. But if I'm sitting here, I'm like, do I feel anything pushing me up? Well, I can feel the floor in my feet, right? I can feel it under me. And I also can tell that I'm being pulled down towards that floor. There's kind of forces acting on me in the up and down direction. Now, we're going to start identifying those sources, but I usually think that it's helpful to actually go all the way down to the bottom and fill out that section below before we go back and identify our forces. So let's do that right now. Before we do that, though, I like to redefine forces and say a force is really just a push or pull on an object. That's what we're comfortable with, having talked about the mass before, right? It's just something pushing or pulling on an object. Our lives have been full of forces so far, and we just never actually really knew it or thought about it. All right, let's go on down to that bottom portion about balanced and unbalanced forces. So, let's talk about balanced and unbalanced forces. Throughout our lives, we've always experienced things pushing or pulling on things, and those forces either make something go at a steady speed or they make it change speed. Right? If you're thinking about being out riding your bike, right? If you're out riding your bike, you're riding at a nice, comfortable speed, you're going at a constant velocity, you're pushing still, you're pedaling, there's a force acting there. But if you want to change your speeds, you have to do something, right? If you want to make your bike go a little bit faster, you're going to have to push harder, right? And you're going to have to increase that amount of push that you're giving to the bike, or increase the amount of force that you're applying in order to make your bike change speed. But when you were just pedaling at a constant speed, you still had to be applying a force to go at a constant speed. So what's up with all of this? Well, whenever we have forces that are balanced, we have constant velocity. This is when you're riding on your bike, you're riding at a steady speed, you're pedaling, that means you're applying a force, but friction, the resistance inside the mechanisms of the bike, is resisting that forward motion. It would slow you down if you didn't keep pedaling just as hard as that pushes back. So when we have constant velocity, we have an acceleration of 0 meters per second squared, and we have balanced forces. What I mean by balanced forces is that the force being applied, that is the force that you're doing, this you pedaling on your bike, is equal to the force resisting motion. That means that when you're biking along there, if you have balanced forces, you pedal, the bike pushes back just as hard as you're pedaling, and your speed never changes. You go at a constant speed. But if you unbalance those forces, you start pushing harder than the bike is pushing back, then we get changing motion. Notice that I didn't just say acceleration, you get changing motion, because a lot of times people associate acceleration with speeding up, in physics it means speeding up or slowing down. What this means is our acceleration is not 0 meters per second, and that means our forces are unbalanced. these are kind of a chain of thought that can help you determine if you have balanced or unbalanced forces. Anytime you see changing motion, you know that your forces are not equal to each other. However hard you're pushing on the pedals of your bike in this case is not equal to however much the bike is resisting you. If you're speeding up, that means that you're pushing harder than the bike's resisting. If you're slowing down, that means the bike is resisting more than you're pushing. That's our changing forces. So, if you have balanced forces, that means your acceleration is equal to 0 meters per second squared, which means that you are moving at constant velocity. Don't worry, I'll take care of that baby in a second. Which means that your forces are balanced. It's a little circle that you can go in to determine if your forces are balanced. The way you tell if you have unbalanced forces is if your acceleration is anything but 0 meters per second squared, or you're not at constant velocity. You're either speeding up or you're slowing down. So, balanced forces, acceleration is 0 meters per second, constant velocity. Any of those conditions are true, the other two are also true. If you have unbalanced forces, you know that your acceleration isn't 0 meters per second squared. It's something. It's going to be some value. And it also means that you either have to be speeding up or slowing down to have unbalanced forces. All right. So now that we've determined that balanced forces cause constant motion and unbalanced forces cause changing motion, we can talk a little bit more about the different kinds of forces that would cause that constant motion or changing motion. So, the first force I want to talk about is gravity, because gravity is fundamental. It is always around us. We're going to represent that force with the label Fg. Now, that label Fg just represents the force of gravity. The force of gravity always pulls us down. It only acts in one direction. It's going to be important to know because we're going to put it on most of our diagrams. It always points down. It really is related to where you are, always present. If you're here on Earth, gravity is happening. Even if you move far away from the Earth, there is still going to be a force of gravity. It's just going to be a whole lot smaller. But force of gravity always points down. Now, the next thing we've got here is what's called the normal force, or Fn. And this is where we can start to think about that balanced and unbalanced forces thing. So when we earlier were talking about balanced forces involve constant motion. Right now, standing here, I know that gravity is acting on me. Gravity is pulling me down. So, if only gravity acted on me, I'd have an unbalanced force, right? I would have to be accelerating downwards, going down. That would be bad. Me and my son would fall straight through the floor. That would be crazy. He's even unhappy about it. Really, what it is though, is that it is balanced. The force of gravity is balanced by what's called the force of normal, or the normal force. See, when things are normal, he's a lot happier. Normal forces are what keep objects from passing through each other. Sorry about that, folks. So normal forces keep objects from passing through each other. If you're a fan of, say, the Marvel movies, you might recognize the Vision as someone who passes through objects. I like to think of that as some great comic book action, but also as a character who gets to ignore the normal force. Now, in the real world, we don't have things that ignore the normal force. It's the force that is from intermolecular, it's basically the force of two objects refusing to pass through each other. We could talk about it down at a smaller scale, but that's not something we need to cover in physics here. One thing you might want to notice about the normal force is when an object's on a surface, it resists gravity. Fn resists Fg whenever an object is on a surface. Alright. Okay, so we talked about the force of gravity and the force of normal, two things that often balance each other. Right now, the force of gravity is pulling me down, but the force of normal is equal and opposite to the force of gravity. It is balancing out that force and keeping me at a constant velocity of 0. Now, if I was to say start moving or go ride my bike, there would be more forces to deal with, right? Gravity would pull me down, the normal force would resist, but if I was riding along on my bike and I took my feet off the pedals, I'd eventually slow down. Well, that would mean that if I'm slowing down, there have to be unbalanced forces. If I'm not pedaling, something needs to be acting on that bike to cause that changing motion, and that is the force of friction. The force of friction always resists motion. This is present throughout our life, and we need it to have most things occur. A friction-free world isn't as great as it would sound. When you're walking along and you feel your feet pulling along the ground, friction is there helping you move forward. Friction is resisting your foot just sliding away. It allows you to pull yourself forward. So in our class, what this is going to mean is that the force of friction, if you have an object that's moving one direction and we tell you friction is present, well, friction is opposite the direction of motion. Opposite the direction of motion. The other thing that we do sometimes is sometimes it's ignored in a problem. You want to look for that wording. So make sure to always look carefully at your problem. Sometimes we're going to put you on the ice, and we'll talk about a hockey puck sliding along a surface of ice, and we'll say, ignore friction, because that's a scenario where there isn't a lot of friction in the real world. Or we'll do it so that we can simplify a diagram or a drawing. Next force we have here is tension, F-T. That's the force of tension. And you might be like, well, what is that? I've heard of that. I've heard that word tension before. So the force of tension is going to be a force applied through a cable or string. Really any non-rigid means of applying that force. So it's a force applied through a string. I was just realizing I always use examples from the classroom. We have those hanging power outlets in our physics room. And I always talk about those as an example of tension. So anywhere you look, no matter where you are, if you see a string holding something up, if you are this winter going sledding and pulling someone on a sled with a rope, that is the force of tension acting there. Last thing we have is the applied force, or FA. This is a force that causes motion. Now, we could model other forces as FA. Sometimes we'll have a tension force that is causing motion, and that is the force of tension causing motion. But since we can specify it, we'll call it FT if we know it's a tension force that's causing motion. This is most commonly seen with pushes and pulls, or uncategorized forces. So this is you're pushing a box with 10 newtons of force. Well, you're pushing with 10 newtons. That sounds like a force you are applying to make motion happen. So it's good for uncategorized forces. So, that's that page. We're still recording. Good. Okay, so let's go and let's take a look at this in action. Now, we've talked a little bit about the different types of forces that can be causing motion and resisting motion and that can come into play on our diagrams. And now we need to go and look at how we actually draw this. So in our free body diagram examples on page 3, we're going to start out with an object that's just sitting there on a nice flat horizontal surface, and it is not moving. It's sitting still. So if I'm thinking about this, I might just be thinking about a book on my desk. Well, if I'm looking at that book, I'm like, okay, I'm going to ask myself this question. Self, what is pushing or pulling on that object? Is anything pushing to the side? No, it's just a book sitting on my table. Nothing's fighting it really either. There's nothing causing or resisting motion there. All right. Well, is anything pulling my book down? Yeah, gravity. Gravity has to be there. All objects on Earth experience the force of gravity. So gravity's pulling it down. Now I have to ask myself, is it experiencing constant motion or changing motion? Well, right here it's a book just sitting on a table, not moving. So that means it has constant motion. So if it has constant motion, that means it has balanced forces. So if it has balanced forces, something needs to be there to balance out the force of gravity. And one thing I think about is, it would be really freaking weird if that book just kind of sunk through the table and just started speeding up, falling towards the center of the planet. That would be weird. So something has to keep the world normal, and that is our normal force. It's not the hero we asked for, it's the hero we needed. It is keeping things from passing through each other. So that normal force right there balances out the force of gravity. We have those balanced forces we needed for constant motion, in this case, a constant motion of being stopped. Right? Keep in mind, stopped is a type of constant motion. Anytime you have an object at rest, you have balanced forces. So this next one, you're going to have constant velocity. Constant velocity tells us that we also are going to have balanced forces. So, if I have balanced forces, I'm just going to go through this and I'm going to ask myself a few questions. Right? And for this one, if I want to think about something moving at a constant velocity to the right, I like to bike. It's nice weather out to be biking, so I'm going to be thinking about me out on my bike going for a ride. So I'm picturing I'm on my bike, I'm pedaling along, I can feel gravity pulling me on down because I'm on Earth. Wish I could bike in space, but that's not really an option. Gravity's pulling me down. Now, what's resisting that motion is the normal force. That's keeping me from going right through the path. That would probably surprise some of the people out there if I just sunk through the path as I was riding along. It'd be pretty sweet. It'd also be easier to social distance. That'd be awesome. But those forces are balanced because I'm not going down, I'm not going up. What I am doing is I'm riding along at a constant speed. In order to do that, I have to pedal or apply a force. And that's where our force applied comes in, right? This is a force that I'm not categorizing as tension or friction.
All right, so that applied force of me pedaling on the bike is going to be balanced by a force because we are traveling at a constant velocity. That force that it is going to be balanced by is the force of friction, right? As you're pedaling, you're applying a force, and you can feel that the resistance inside the bike resisting your motion, applying a force backwards to balance out the force that you're applying when you're pushing on the pedals. If you took your feet off the pedals and you stopped pedaling, you'd lose your applied force, the force of friction would take over, and you'd have an unbalanced force and slow down. You're going to try to make sure your arrows are the same size when you have balanced forces, like in this case with force applied and the force of friction. Okay, let's take a look at an object accelerating to the right on a horizontal surface. So this would be like you in a car at a stoplight. Light turns, you put your foot down on the gas, and you begin accelerating. Anytime we are accelerating, that means that we have unbalanced forces, because anytime we have changing motion, that is acceleration not equal to zero, we have unbalanced forces. They all kind of go together. Changing motion, A is not equal to 0, unbalanced forces. That's going to tell us things about what we need to draw on our free body diagram. So one of the things we're going to do when we draw arrows for unbalanced forces is we are going to make sure that we really accentuate the size of the arrows when we are drawing them. That way when we're going in and grading them, we can see it. So right here, we're thinking about maybe we're out on our bike still, and we're riding along. We're still affected by the force of gravity. That's never going to go away. Now, depending on which physics teacher you have, you may or may not need to draw that on every one of your diagrams. If you have Mr. Trago, you're going to have to draw FG and FN on every one of your diagrams because they are there, unless it's a falling object. Right? FG and FN are paired up on horizontal surfaces or anytime an object's sitting on a surface. Now, as we are biking along and we are accelerating to pass someone, we are going to have to think about biking, right? You're going to have to push a lot harder on those pedals if you want to change your speed and accelerate. So we're going to make that arrow really big because we want that arrow to really represent that our force applied, the force of us pushing on the pedals is a lot bigger. Now, just because we're pushing harder doesn't mean the force of friction really increased by any amount, right? So we're going to leave the force of friction arrow the same. And in this diagram, we can really clearly see that one arrow is much larger than the other arrow. I know that, in pretty much any situation where we have balanced or unbalanced, you're going to try to either make them almost exactly the same size for balanced or one way bigger for unbalanced. It's going to make our lives way easier as graders. Right? So that also fits with unbalanced. If we put those side by side, right, one would be bigger than the other. They would tip it. All right, so the next type of motion we need to talk about are the two types of falling motion that we are going to look at in physics. We're going to be looking this year at free fall and terminal velocity. Now, free fall and terminal velocity are both things that we can see exhibited by pretty much anything like a piece of paper falling, or what's more fun is talking about skydivers. All right, so when we are looking at people skydiving, they're going to start out exhibiting free fall, and as they fall, they're going to move towards exhibiting terminal velocity, right? Anytime we drop an object, this is going to be true for it as well. I really miss getting to drop tons of stuff in the classroom and really accentuate some of this stuff as I do it. Now, when we have an object experiencing free fall, that object is experiencing the force of gravity as it falls, right? This is like someone when they just jump out of an airplane. As they fall, they start out experiencing only FG, but swing your hand through the air a little bit, you're going to feel a certain amount of resistance or friction between you and the air. What this means is that air will resist motion, causing that friction that resists motion anyway. When you first get out of a plane and start falling, or when a piece of paper starts falling, that friction isn't going to be super high. However, as you continue falling, it will increase. So at the start of our diagram, during free fall, what we are going to do is we are going to draw a force of friction arrow that is a lot smaller than the force of gravity arrow. Man, just watching as I dub myself here, I look absolutely ridiculous swinging my hand around like that. Eventually, I will stop being so long-winded and draw that small force of friction arrow. There we go. Sorry, dubbing is kind of weird. The key thing to remember with free fall is that the force of friction is less than the force of gravity. When someone is experiencing free fall, their velocity is increasing as they fall downwards. When you're at free fall, you are speeding up. This means that you have unbalanced forces or changing motion. That also, as a reminder, means that when we have unbalanced forces, changing motion, our acceleration is not equal to 0. Now, eventually I'm going to get on here and I'll talk about terminal velocity. In the background here right now, while we're waiting for me to get about it, you can hear the reason why this is a dubbed over version of my notes. Now, if you are going to remember one thing and nothing else about free fall, it's that it is an unbalanced force. All right. Now, as people start falling when they're skydiving, eventually they're going to reach a terminal velocity or a constant velocity. You'll see skydivers will sometimes spread out their arms to change this velocity as well, so that they are no longer increasing their speed by as much. They're changing the amount of force that is balancing their falling motion. As you fall, when you reach terminal velocity, the force of friction with the air has increased. You probably have felt this before. If you stick your hand out of a moving car, you're going to feel a lot of air resistance. The faster you go, the more friction there is. So at terminal velocity, the force of friction with the air has grown to such an extent that it is now balanced with the force of gravity. Anytime we have balanced forces, we have constant motion, or an acceleration of 0 meters per second squared. So if you remember nothing else about terminal velocity, remember that the forces are balanced. If you are wondering why the forces are balanced, it's because the faster you go, the more friction there is. Once those forces are balanced, because friction has equaled to gravity, it won't speed up anymore because your speed won't be increasing to increase the force of friction. You've now just got balanced forces, and that skydiver is going to fall at a constant velocity for the rest of its motion. One thing that we're going to be doing for you here this year is we are going to be cutting elevator problems. We felt like this was just one too many types of problems to do when we're online. If you see any elevator problems left in our packet or in our problem sets, please just remember we will be skipping elevator problems this unit. It's just one of the things that we discovered as we kept moving. We felt like it was a little bit unnecessary to cover when we're online in the interest of keeping your lives manageable. We're doing the same thing with Atwood's machines since it's another type of elevator problem. So those Atwood's machines will also be crossed out. Anytime you see an elevator problem or an Atwood's machine problem, go ahead and skip them. Or if you're looking for a challenge, reach out to your teacher and we can do a quick explanation video for you.